Hi everyone. In this video we are going to discuss three different examples, right? They have a common question: determine the nature of singularity of the following function. So we know that when we say the particular point is a singularity of a given function, if the function is not analytic, at that point then we say it a singularity. Okay, generally what we say, if the denominator for particular point denominator is 0, then it is a singular point. For example, if I put z is equal to minus 2 plus 2, 0, that means for z is equal to minus 2, denominator is 0, so it is a singular point. Okay, but actually the main task is to find the nature, that means a type of singularity. So there are several types of singularities. Okay, in previous video we have already covered, but let us recall all those types and then we will start to solve problems, right? So generally what we do, we try to express the given function in a form of Lorentz series. Okay, so what is the standard form of Lorentz series? Summation an z minus z naught raised to n plus summation bn upon z minus z naught raised to n. So Lorentz series has two parts. This is analytic part and this is principal part, right? Actually the principal part is so much crucial for us. Okay, by observing the principal part we will decide the type of singularity. See, the analytic part will be there, okay, for each and every function, but in case of principal part, if you have b1 upon z minus z naught plus and so on, bn upon z minus z naught raised to n. So this is the last term, getting all remaining terms are 0. That means that principal part terminates at nth power, getting this one. Then we say it is a pole of order n. This is a pole of order n, getting. So that means if the principal part having a finite number of terms, then we say it is a pole of order n. If the principal part having infinitely many terms, how many terms are there? Infinitely many. Bn z minus z naught raised to n. Again there are infinitely many terms, then we say it is isolated essential singularity. What we say? Isolated essential singularity. If the principal part is 0, then we say it is removable singularity. What we say? It is removable singularity. And there is one more singularity which is non-isolated essential singularity. In case of non-isolated, we do not go for Lorentz series. We get a sequence of points, all these are singularities, converges to z naught. Then we say that z naught is non-isolated essential singularity, but there are very few examples we have of this one. In most of the cases, we go for Lorentz series, and by observing principal part, we decide what is the type of singularity. Okay, I will do the same thing for all these problems. Okay, so let us start to do. Let me remove this part, it is not required. Okay, just a minute. I will make it clean and then we will go further. So let us start to discuss this example. Okay, what is the function we have? Let me call it as f of z. So we have this is our function. So f of z is z plus 1 sine 1 upon z plus 2. Tell me what is the singular point, that means for what value of z denominator will be 0? Obviously minus 2. If I put minus 2 here, minus 2 plus 2, 0. Oh, let me clearly mention, clearly z is equal to minus 2 is a singular point. Okay, so now let us start our main task. We have to find the Lorentz series and we will find its type. Okay, type of singularity. See, so f of z, let me write again, f of z, what we have? Z plus 1 sine 1 upon z plus 2. So we have to find Lorentz series at z is equal to minus 2. We want Lorentz series about what? Z is equal to minus 2. So when you want Lorentz series about z is equal to minus 2, that means z plus 2, by shifting minus 2 on this side, you will have this bracket z plus 2. This bracket should appear everywhere, getting z plus 2 should appear. So z plus 2 already we have. So we need to think about this bracket only. We should adjust z plus 2 here. Tell me how to adjust z plus 2. It's quite simple, no? Z plus 2 minus 1. 1 was already there. 2 minus 1, 1. Okay, so in this way I have adjusted z plus 2 sine 1 upon z plus 2. So let us multiply and make them separate. This bracket into sine, okay, and minus 1 into sine, so you will get sine 1 upon z plus 2. So now what will I do? We have standard expansion of this sine z. I am going to use it. What is it? Let me write here. See, when you have a standard functions just like sine, cos, log, e raised to z, 1 upon 1 plus z, 1 upon 1 minus z, then we directly go for their series. Okay. So series of sine already we have. Let me write here. Sine z is z minus z cube by 3 factorial, z raised to 5 by 5 factorial, and so on. Okay, so this is standard series of sine z. Same series I am going to write for them. So this is equal to z plus 2. What is the difference? At a place of z we have 1 upon z plus 2. This is the only difference. So let me write. Z is there, that means 1 upon z plus 2 minus 1 upon 3 factorial. It is in denominator, so that z plus 2 cube will appear in denominator. It is already in denominator now, so z, that bracket will be in denominator, plus now fifth power 1 upon 5 factorial, z plus 2 raised to 5, and so on. It's over. Get it? Minus sign is there, and again we have to write the same series. So let me write same series. Okay, 1 upon z plus 2 minus 1 upon 3 factorial z plus 2 cube plus 1 upon 5 factorial z plus 2 raised to 5, and so on. Okay. So what is the difference here? We have z plus 2 is a multiple of this bracket, and there we have a single bracket. Getting? Now what will I do? I will take product, okay, of each term of this bracket with z plus 2. Let us see what will happen. See, this series is not required. Let me remove this one. So we will have some more space to write. Let us see what will happen. This is equal to z plus 2 into 1 upon z plus 2. That means z plus 2 upon z plus 2. Directly also you can solve, okay, but I am writing each and every step. Minus product of these two, that means z plus 2 upon 3 factorial, z plus 2 raised to 3, plus product of these two terms will be z plus 2 upon 5 factorial, z plus 2 raised to 5, minus. So let us talk about this bracket now. So we have minus sign outside the bracket. So when you solve the bracket, all sign will get changed. So 1 upon z plus 2, agree? Minus minus plus 3 factorial z plus 2 cube, plus minus minus 1 upon 5 factorial z plus 2 raised to 5. So this is equal to bracket cancel 1 bracket will get cancelled, 3 factorial z plus 2 square, since by cancelling one bracket we will have this. Here one bracket will get cancelled again, z plus 2 z plus 2. So we will have 1 upon 5 factorial z plus 2 raised to 5, and so on. Here we have minus 1 upon z plus 2 plus 1 upon 3 factorial z plus 2 cube minus 1 upon 5 factorial z plus 2 raised to 5. Okay, this is equal to, okay, let me write in a proper way. I will write in a way that is with increasing powers of that z plus 2. So let me write 1 first. This bracket has power 1, so 1 upon z plus 2. After that I will write this bracket since it has power 2. In this way I will go with the increasing power of that bracket. So minus 1 upon 3 factorial z plus 2 square. After that let us write this 1 upon 3 factorial z plus 2 raised to 3. See, I think here we have a 4 now by cancelling one bracket. By cancelling one bracket, power 4. So plus 1 upon 5 factorial z plus 2 raised to 4 and so on, okay. Yeah. So tell me which type of singularity is this one, z is equal to minus 2. What do you think? What is the principal part? This is a principal part. No, why we are saying it is a principal part? Since that bracket appears in denominator, it is in denominator, so that's why it's a principal part. This is in principal part, this is also, all terms lies in principal part except this one. So how many terms are there in the principal part? Infinitely many terms are there. It is not terminating anywhere, getting? Infinitely many terms are there. So that's why if principal part of Lorentz series expansion has infinitely many terms, then we say it is, what we say? Isolated essential singularity. So that's why we will declare z is equal to minus 2 is a isolated essential singularity. Just make a screenshot of it, I will write and then we will go further. So I have clearly mentioned there, Lorentz series expansion, this Lorentz series expansion has of f of z has non-terminating principal part. It is not terminating in any area, infinitely many terms are there. So that's why z is equal to minus 2 is isolated essential singularity, okay. Just make a screenshot of it, then we will go for the second example. So let us discuss this second example, okay. What is the second example? Let me write f of z. F of z is equal to z square e raised to 1 by z, okay. See, first of all we have to find its singularity. That means a point where function is not analytic. Generally you can say the denominator is 0. Tell me for what value of z denominator will be 0. So the first of all there is no any denominator, getting, but power of e has some denominator here. So if I put z is equal to 0 there, that in power denominator will be 0 and we say the function won't be analytic. So let me clearly mention here, z is equal to 0 is a singular point. So this is a singular point, okay. And now we have to find its type of singularity or the nature of singularity. So the most important task is to find Lorentz expansion of this function f of z at z is equal to 0. That means we want z everywhere, getting? So let me tell you one thing, many times students get confused. So when you have to find, okay, when you have to find Lorentz series about z is equal to z naught, then z minus z naught, this bracket should appear everywhere. But see, when you have to find Lorentz expansion about z is equal to 0, that means z minus 0, that bracket should appear. But z minus 0 means z itself, no? So that means simply z appears everywhere, okay? So no need to take tension, no need to worry when you have to find the Lorentz series expansion for z is equal to 0. But see, if other than 0 you have some point 2, 3, minus 1, minus 2, in that case you need to take care of it, okay? So here the problem is quite simple, since 0 is a singular point and we have to find Lorentz series expansion. So let me write f of z here again. What is f of z? Z square e raised to 1 by z. So we are familiar with a series expansion of e raised to z, which is 1 plus z square by 2 factorial, z cube by 3 factorial, agree? Z raised to 4 by 4 factorial and so on. But see, in power of e we have 1 by z. Here what we have z, here what we have 1 by z. That means at a place of z we have to write 1 by z. This is the only task. Let us use this series. Z square, okay, 1 plus, try to say, okay. So what will I get here? 1 by z. So here 1 by z is there. So that's why z square will be in denominator. 1 upon 2 factorial z square, 1 upon 3 factorial z cube, 1 upon 4 factorial z raised to 4. This kind of series we will have. Let us solve the bracket. That means I will take the product of this z square and each term of this bracket. Let us see what will happen. Z square into 1, z square into 1 by z, z square by z, z square by 2 factorial z square. Take the product of this one and this one, z square by 3 factorial z cube, z square. Okay, let me remove this part. We understood, I hope, this series. Z square by 4 factorial z raised to 4 and so on. So here z square we can cancel in most of the cases it is possible. So z square plus z cancel, z only, z square cancel 1 by 2 factorial, z square cancel 1 by 3 factorial z square cancel 1 by 4 factorial z square. This kind of series we get. So let us find the principal part and analytic part. Principal part, that means that z appears in denominator. Here z is in denominator, here also z is in denominator. So this is what? Principal part. Analytic part, that means z appears at numerator. So this is the analytic part. Okay, how many terms are there in a principal part? Infinitely many terms are there. Getting it is not terminating anywhere. So which kind of singularity? It is isolated essential singularity, since that analytic principal part has infinitely many terms. Let me mention Laurent series expansion. Laurent series expansion of f of z about z is equal to 0 has non-terminating principal part. See, in another way you can say, that is infinitely many bns are non-zero. Infinitely many bns are non-zero. Therefore, z is equal to 0 is an isolated essential singularity. Okay, yes, so in this way we proved it is isolated essential singularity. Okay, one more example we are going to discuss. Just make a screenshot of it, then we will go further. So let us discuss this third example. Okay, so let me write first. This is our f of z. We have, what is f of z? It is 1 minus e raised to 2z upon z cube. So our first task is to find its singular point where the function is not analytic, or the point where the denominator is 0. You can easily see for z is equal to 0, denominator will be 0. So 0 is a singular point. Let me clearly mention. Clearly, z is equal to 0 is a singular point. Okay, it's a singular point, right? So now we have to find its type, nature of singularity. Which type of singularity is this one? It is a removable singularity, it is isolated essential singularity, it is non-isolated essential singularity, or it is a pole of order n. Getting? So for that we need to expand in a form of Laurent series. Okay, so let us expand in a form of Laurent series at z is equal to 0. So simply in a form of z we will have. So let me write f of z 1 minus e raised to 2z upon z cube. This can be written as 1 by z cube 1 minus e raised to 2z. Okay, so when we have, in a function, when you have exponential function, when you have sine z, when you have cos z, when you have log z, when you have 1 by 1 plus z, or when you have 1 upon 1 minus z, then we go for a standard series. So here also we have exponential function, so I will use its standard series. You remember its standard series, e raised to z, what is it? 1 plus z square by 2 factorial plus z cube by 3 factorial. So this is a standard series. Getting? So let me write its expansion 1 upon z cube 1 minus in bracket e raised to 2z. See, what is the difference? Here we have z, here we have 2z. That means at a place of z we should write 2z. Okay, 1 plus 2z plus 2z square, that means square of 2 as well as square of z. So we will have 4z square by 2 factorial. Next 2z cube, that 2z at cube means 8z cube by 3 factorial. I am taking the power directly here and I am writing. Okay, so let us write few more terms. Fourth power of 2 is 16 z raised to 4 by 4 factorial. Fifth power of 2 is what is it? 32 z raised to 5 upon 5 factorial, and so on. Okay. So let us solve the bracket. Let us use this space, okay, to solve the remaining part of the problem. 1 by z cube. Will you guess what I need to do? My next task is to solve this bracket. That means, see, minus sign is there outside the bracket. So when you solve the bracket, when you remove the bracket, all sign will get changed. 1 minus 1 sign, all here we have a plus sign, so all will be minus. Minus 2z minus 4z square by 2 factorial minus 8z cube by 3 factorial minus 16z raised to 4 by 4 factorial minus 32z raised to 5 by 5 factorial, and so on. See, this plus 1 minus 1 will get cancelled. So my next task is to multiply each term of this bracket by 1 by z cube. It is in denominator, that z cube is in denominator, so it will be in denominator if you multiply. So we'll have like this, minus 2z upon z cube minus 4z square upon 2 factorial z cube minus 8z cube upon 3 factorial z cube minus 16z raised to 4 upon 4 factorial z cube. It is in denominator, so when you multiply, it will be denominator again. 32z raised to 5 upon 5 factorial z cube. Tell me, can you cancel anything here? Yes, obviously. Z we can cancel, z square we can cancel from numerator denominator, z cube will get cancelled, z cube will get cancelled. Okay, let us write minus 2 upon z square minus 4 upon 2 factorial z cube cancel minus 8 upon 3 factorial 16z cube cancel, 1 z will be there in numerator, z square cancel, 32z upon 5 factorial, and so on. Okay, so let us find its analytic part and principal part. Analytic part, that means that term z appears at numerator. Z appears at numerator, that means is, yeah, in all this part z appears at numerator. Okay, and principal part, so this is analytic part, right? And principal part, that means z appears in denominator, so this is a principal part. Since that z appears in denominator, tell me how many terms are there in principal part? Only 2, 1 and 2. So if the principal part having finite number of terms, getting principal part having finite number of terms, then what we say? It is pole, getting, it is a pole. And what is its highest power? 2 in denominator, so therefore it is a pole of order 2. So principal part of Lorentz expansion has finite number of terms so therefore z is equal to 0 is a pole of order 2 since the highest power is 2. Okay, so in this way we have discussed all these 3 examples. Just make a screenshot of it, then we will stop. Thank you. See you in next video.